Okay. All right. Theorem is this. If alpha is a curve, is a regular curve, sorry, regular curve in R3, then there exists a parameterization, reparameterization beta of alpha, so that beta has unit speed. The statement is, of course, is something very natural. If you can move on a curve without stopping, if your velocity is always non-zero, then you can arrange so that your speed is always 1 unit, right? That's what it says. But let's see if it is, possible mathematically. Suppose your curve is this. If alpha is your curve, let st be the distance traveled. St is this. I measure from A, some point, up to t, and then alpha prime t dt. So you integrate from, okay, I should say, let's say d alpha prime u du. Okay, the distance, what is this? The distance traveled from t equals a to t. Yani t eşittir a'dan t'ye kadar olan zaman içinde, değil mi? Şurası alpha a, this is alpha t, so this is the point t equals a, and st is nothing but the distance traveled. You integrate your speed, okay? The distance traveled. Clearly, the derivative of this, right? This is a function, and from the fundamental theorem of calculus, its derivative, since it is defined via this rule, what is the derivative of this? It is just this continuous function evaluated at t, right? So it is just alpha prime t. So it's a differentiable function with derivative alpha prime t. Okay. Now define beta s. So I am using a different parameter as this. So alpha of ts. Where pardon, bunu söylemeden önce şeyi söylemem lazım. Tabii bunun inversion, özür dilerim. Sorry, I forgot a line. Well, this gadget is always positive, right? Since the curve is regular, this is always positive for all t. And since the derivative is always positive by the inverse function theorem, this function is invertible, right? It has an inverse. Since the derivative is always positive, so by the inverse function theorem, TS, no, S is has an inverse. Actually, you don't even need inverse function theorem. The idea is very simple. Suppose this is your T, this is your S. Derivative of this function is always positive. Means, its graph is like this. Suppose you are on an interval like this. So, sorry. Yeah, it is always increasing, right? It's increasing. It's something like this. Well, okay. Something like this, right? It's always increasing. Therefore, it is one-to-one, right? If it were not one-to-one, then by the mean value theorem, the derivative should be zero at some point, but it is one-to-one. So S is one-to-one. And clearly onto its image. And the derivative is always positive, it's differentiable. Therefore, the inverse function theorem tells us that it has an inverse. And the inverse function, let's say T equals TS. So I write this time T as a function of S, okay? Is also differentiable. And it's continuous, of course. And actually, what is dt ds? Well, it is just 1 over ds dt. Değil mi? Bir fonksiyonla onun inverse'ünün derivatifleri de birbirlerinin tersi, right? This is because from the following fact. If f and g are inverse of each other, let's say like this for all x, and if they are both differentiable, when you take the derivative of this, you get f prime gx times g prime x is equal to derivative of x, which is 1. Therefore, the inverse function has derivative, which is just 1 over the function itself. Right? The derivatives of f and its inverse are reciprocals of each other. All right. Okay. Let me erase this board. So this function has an inverse. Actually, practically, we know already this because, time measures the length traveled, right? So well, this function, yeah, you are right, but actually there is no mistake here. You are right because the statement is a local inverse, but here this function is increasing for all t. Its derivative is never 0. Therefore, it has a global inverse actually. Since it is one-to-one, it is, you are right, it is an inverse. But to be able to say something about maybe its derivative, Well, you don't need maybe the full strength of inverse function theorem, but I mean, at least you need to have this, you know, formula for the derivative. Şunun için aslında you need to be able to compute this. You have to know that the inverse function is invertible. This tells us that, you know, inverse function exists, but it is just a function. To say that it is continuous or differentiable, actually you need the power of inverse function theorem. Otherwise, you cannot do this computation. Okay. Bu ekran gene donmuş. Okay. Bunda bir gariplik var ama neyse. Okay. All right. Now, şimdi beni görüyor. Let beta s to be this gadget, alpha of ts. So, instead of the parameter t, I am using the parameter s. I put s inside this function. And then I put t inside alpha. Then, since both alpha and t are differentiable, b is differentiable. B is differentiable. And what is derivative of this? Okay, derivative of this. So beta is nothing but alpha, but you put another parameter in it. Okay, so it's a reparameterization of alpha. It's the reparameterization of alpha, and its derivative is what? Well, this is just alpha prime ts times derivative of inside, so dt ds. But alpha prime is just well, dt ds is what? Well, the norm of this is this. Norm of alpha is just ds dt. ds dt. They are all positive, so, and then also positive dt ds, and this is equal to 1. Yani şöyle yapıyorum aslında, bu çarpımın normunu alıyorum. But this is a positive number. I can take it outside, but then this is just norm of this is just ds dt, so it is just 1. So you see that beta is a reparameterization of alpha, and its speed is always 1 for all s. Okay, hence we are done. Okay, this finishes the proof. Okay. An example. Let's consider this curve alpha t. This is the helix we have here. A cosine t, a sine t, and for some fixed constants A and B, A, B, which are both, let's say, positive or non-zero. Then alpha prime t is what? Alpha prime t is just times A times C, A times cosine t, and therefore the speed of this curve is just length of this vector, square of this A squared sine squared, A squared cosine squared, that A squared, and then B squared. So I have A squared plus B squared. So the speed is constant, right? Is constant for all t, but it is not necessarily one, right? It can be any number depending on A and B. How can we make this unit speed? Well, let's see. Proof of our theorem gives us how we can do this. So we have to compute the function s. So what is s? St, this is just from any point, let's say from 0 up to t, alpha prime u du. Well, this is 0 to t, alpha prime. Alpha prime is always a squared plus b squared. So this is just a squared plus b squared. I have du. This is just a constant. So a squared plus b squared. Integral of du is just u. So u from 0 to t. So I just get t here. Therefore, our function, arc length function, is just this constant times t. It is invertible. I can write t as a function of s. What is t as a function of s? T is just as a function of sts. And what is that function? T nedir? 1 over a squared plus b squared times s. Right? So t as a function of s is equal to this gadget. In this case, you know, functions are kind of easy. Both ts and st are just linear functions. So what is beta t? Sorry, beta s. Well, beta is s is just alpha of ts. So alpha of ts. Ts is just s over a squared plus b squared. So inside alpha, instead of t, I will write s over this gadget. So we have a times, right? In this expression, I will replace t by s over square root of a squared plus b squared. So a times cosine s over a squared plus b squared, a times sine s over a squared plus b squared, and b times t, which is s over a squared plus b squared. Okay, now this is the unit speed parameterization of alpha t. Okay. They both parameterize the same curve, this helix. One of them goes with the speed squared plus b squared inside square root. Other one goes with the speed 1. If you compute derivative of this and take the length, you will obtain 1. Okay. I won't do the computation, but it's easy. You know, just take the derivative of this with respect to s, and then compute the length of that vector. You will get 1. Well, unique up to shift, I should say. You know, if you replace this parameter s by s plus 1, speed won't change. Also, yeah, you can do something like this. It means you are going backwards, the same curve backwards. Yeah. Except those, it is unique. Yani bir yolu, değil mi? Birim hızla gidiyorsanız kaç değişik şekilde gidebilirsiniz? Yola ne zaman çıktığınız da önemli. Değil mi? Saat 2'de mi çıktınız, 3'te mi çıktınız? Çıktıktan sonra artık nereye gittiğiniz belli. Unit hızla gidiyorsanız. Bir de tabii ne yöne gittiğiniz. Hani Eskişehir-Ankara yolunda gidiyorsunuz ama hani Eskişehir'e doğru gitmeyebilirsiniz. Aynı yoldan başka istikamette de gidebilirsiniz. Yani ters istikamette gidebilirsiniz. Yani shift ederseniz de hızınız değişmez veya parametreyi eksiye çevirirseniz, yani geri giderseniz de hızınız değişmez. Velocity değişir ama hız değişmez. Tamam mı? Okay. Let me erase this part. Okay. A vector field y on the curve, let's say alpha, is a function that assigns to each t in the domain a tangent vector yt to R3 at the point alpha t. So what's the vector field along a curve alpha t? It's something like this. Suppose your curve is like this, alpha t. At any point, okay, you assign a vector this to the tangent space at this point. Let's say alpha t is this point. The tangent space at this point to R3 is a three-dimensional vector space, right? It is R3, and you just pick a vector. Okay, you just pick a vector, any vector you want. It can be something like this, yt. The only requirement is that yt has to be at the tangent space to R3 at the point alpha t. Yani alfa t noktasında bir vektör seçiyorsunuz. If you choose a vector for each point of this curve, you obtain a vector field on the curve alpha. Yani bunun her noktasına bir tane vektör seçiyorsunuz. Sıfır vektör de seçebilirsiniz. Yani şöyle dönen bir şey de seçebilirsiniz. Her noktasına bir vektör seçiyorsunuz. Tamam mı? Okay. We already have a vector field on any curve, actually, differentiable curve. It's velocity vector, right? So, example, if alpha t is a curve in R3, then yt, which is just the velocity vector, is a vector field. On alpha, right? So to each point of your curve, you pick your, so this is the point alpha t, and you pick your vector to be just the velocity vector of this curve. This is a vector field, okay? On alpha. Hız vektörünü seçiyorsunuz. Her noktadaki hız vektörünü. Peki. Well, your vector field, of course, has components, right? Let me call them as y1t, y2t, y3t. Suppose this is a curve, so vector field on the curve alpha t, vector field on the curve alpha t. It's also a function, right? Actually, it's a vector valued function. For each t, you get a vector. In R3, actually not in R3, in the vector space to R3 at the point alpha t. But you know, if you forget this point, you have just a vector in R3, you have just three functions, and you can differentiate them. And that's what we are going to do next. The vector field, the derivative of a vector field is defined as what? Y prime t. Well, you just take derivative of the components of this vector field. Assuming that, of course, they are differentiable, okay? So whenever it means that I assume that it is differentiable, okay? So we don't bother whether it's differentiable or not. They are differentiable as many times as we want, okay? Of course, in general, not all functions are differentiable. Not all curves are like this, but this is the type of curves we are going to study. Yeah, it's another vector field on alpha t. And yt, if yt is this, y prime t probably something like this, right? Y prime t. Because here coordinates are y1, y2, y3. Now they changed, but it's another vector field. It's another vector field. If you take, of course, if this is the velocity vector, when you take derivative, you get the acceleration vector, right? So if this is the velocity vector of your curve, then the derivative of the velocity vector is the acceleration vector. It is something you already know. Ağzınızı görmediğim için kim konuştuğunu anlamadım. Pardon, özür dilerim. Vektör bir noktadaki vektör. Vektör field deyince neyin üzerinde vektör fieldsa, burada dedi ki alfa t'nin üzerinde vektör field. Alfa t'nin her noktasına bir tane vektör koyuyoruz demek. Vektörlerin tarlası yani. Tamam mı? Vektör bir tane ama vektör field deyince tarla. Tarlanız bir eğri de olabilir. Düzlem parçası da olabilir. Tamam mı? Okay. We have a lemma. Let me change the board.
Evet.
Okay. It has 3 parts. A curve, alpha is constant if and only if its velocity vector is 0. Well, of course, this is something trivial, right? If velocity is 0 for all times, then you are not going anywhere, right? It's a constant curve. A non-constant curve alpha is a straight line if and only if its acceleration vector what is the acceleration vector? Derivative of the velocity vector. This is the derivative of alpha, the velocity vector. If you take derivative one more time, it is the acceleration vector. And if this is 0, then of course for all t, then you are moving on a straight line, right? So if you don't feel any force, if you are in a car and you don't see anything, suppose the windows are covered, if you don't feel anything, it doesn't mean that you are stopping, right? You might be going on a straight line with constant speed. Okay, third part, a vector field. Yeah. You are right. I guess I should write here on is a straight line. Yeah. Or we can maybe write it this way. With constant speed. Let me write. On a straight line with constant speed, if and only if its acceleration vector is 0. Okay. Now it's fine, right? A vector field y on a curve is parallel if and only if its derivative is 0. So meaning this for all t. Parallel means what we mean by that is the following, of course. Suppose this is your curve. At each point, you have a vector, and suppose that these vectors are always the same. Okay. You just parallel translate this. Their direction and the lengths are the same. If this is the case, then y prime is 0. Okay. Okay. Well, I guess these do not need a proof, right? I mean, y prime is 0 means the components of this function are constant, right? Therefore, the vector is itself constant. And here you are moving on a straight line. Belki iki için bir şeyler söyleyebilirim. I guess the first one and the third one are clear. One and 3 are clear. For 2, okay, now if first assume alpha t is a parameterization, is a constant speed parameterization of a straight line. Well, straight line means so it is something like this, right? You are at a point, and then let's say, okay, ne olsun nokta, A, B, C olsun. and then plus your speed vector, velocity vector is constant. Ya da şöyle diyeyim yani nokta ve velocity'yi şöyle göstereyim. Suppose you start from the point P1, P2, P3 and then T times the velocity vector V1, V2, V3. So you are at this point and you move with a velocity vector V. Okay, V is this vector and P is this point. Then of course, then what is V prime? V prime is just V and not V prime, sorry. Alpha prime is this, and what is alpha double prime? The acceleration, since this is constant, it is 0. Okay, 0 vector. And conversely, if alpha double prime is 0 for all t, then what is alpha prime t? İkinci türevi 0 olan bir fonksiyon. Birinci türevi nedir? Yani türevi 0 olan bir fonksiyon. O zaman o fonksiyon constant. Değil mi? So if this is the case for all t, then alpha prime t is just a constant vector. Right? A constant vector. But then if this is the case, what will be the alpha vector? Right? Yeah, right? So if the derivative of a function is a constant number, then that function is just a linear function, right? It is just a times t plus some other number. Hence, what is vt? Sorry. Gene dondu bu. Özür dilerim. Bu bazen böyle şey yapıyor. Okay. All right. Alpha t is just the constant vector v1, v2, v3. Hence, alpha prime t. Sorry, alpha prime t is v1, v2, v3. Therefore, alpha t is just plus another number. Let me say p1. No, sorry. P1 plus p1, so that the derivative of this with respect to t is just v1, and then p2 plus tv2, and p3 times tv3. Therefore, this is p1, p2, p3 plus t v1, p2, v3. So if the second derivative is 0, right? If the second derivative is 0, then the first derivative is a constant vector, and the curve alpha is the form. Therefore, it's a parameterization for a straight line with constant velocity. Hence, alpha t parameterization for a straight line with constant speed. Okay. Yeah, I guess we may stop.
Hocam bir şey sorabilir miyim?
Sor.
Lemma'da 2 ile 3 aynı şey mi ifade ediyor?
Lemma'da 2 ile 3
Vektör field'da sonuçta pardon. Vektör field'da biz hız dedik ya.
aha.
Onun türevi
Ama bu
acceleration.
herhangi bir vektör field olabilir. Yani
Yani
şurada
hız bir vektör
mesela
field.
bu velocity vektörü değil. Herhangi bir vektör de olabilir. Herhangi bir vektörün de constant olup olmaması, yani işte paralelden kastettiğimiz o değil mi? Bu vektör hep aynı. Onun türevinin sıfır olup olmamasına denk. Onu söylüyoruz sadece.
O zaman 2'de sadece hız vektöründen bahsediyoruz.
Evet. 2'de sadece hız vektöründen bahsediyorum. 3'te ise aynı şeyi genel bir vektör için söylüyoruz.
Tamamdır. Teşekkürler.
Rica ederim.